Hello, I'm Jishnu Mukoti, and in this video, I'm going to be talking about our paper, Deep Deterministic Uncertainty, a New Simple Baseline. This work was done with my wonderful collaborators, my co-first author Andreas Kirsch, Joost van Amersfoort, Philip Thor, and Jaren Gal. Uncertainty quantification methods like deep ensembles or MC dropout, while effective at their job, are often very resource and compute intensive. This makes deploying them difficult for large-scale tasks like semantic segmentation. In this work, we present a very simple solution to quantifying epistemic and aleatoric uncertainty from a single deterministic model. To achieve this, we have two main requirements. First, we need a feature extractor which is by-Lipschitz constrained, that is sensitive and smooth, ensuring that feature space representations maintain some semblance of distance in input space. Second, with a constrained feature extractor, a density model as simple as Gaussian discriminant analysis can effectively quantify epistemic uncertainty. For a given input, we first check if the feature density is low or high to see if it is out of distribution or has high epistemic uncertainty. If the input is not out of distribution, we check the softmax entropy of the classifier to see if it has high aleatoric uncertainty, that is, if it is a noisy or ambiguous sample. Finally, if the input does not have high epistemic or aleatoric uncertainty, we can safely make predictions on it. We call this simple method Deep Deterministic Uncertainty, or DDU in short. Let's start by looking at what kind of data we can have in deep learning. We can have our clean training data. We can have noisy or ambiguous data in the training set as well, due to observation noise. And we can have data which describe concepts outside of the training set. In distribution data, which are noisy or ambiguous, are cases for which a model should have high aleatoric uncertainty. Such uncertainty is not reducible with more data but can be reduced with less noisy measurements or less label noise. On the other hand, out of distribution data describing concepts outside of the training set are cases for which a model should have high epistemic uncertainty. This can be reduced by training the model with more data. So what are the current state-of-the-art uncertainty quantification methods? Let's look at two of the most popular uncertainty quantification methods out there, MC dropout and deep ensembles. In MC dropout, we conduct multiple forward passes with dropout active at test time, and in deep ensembles, we have an ensemble of models predicting on the same input. For each of these methods, we can use the softmax distribution from each forward pass or each model to compute predictive entropy or mutual information between the model weights and output. Predictive entropy captures both aleatoric and epistemic uncertainty, and so it is high on ambiguous or noisy data as well. Mutual information captures only epistemic uncertainty, so it is high on out-of-distribution points only. So these models can effectively quantify and disentangle epistemic and aleatoric uncertainty. However, as they require multiple forward passes or use multiple models for prediction, on more compute-intensive tasks like semantic segmentation, they often become infeasible to get reliable uncertainties in real time. So our primary motivation here is to get a model which can quantify uncertainty using a single forward pass. For this, the first thing we need is a sensitive and smooth feature extractor. Why? Let's say we have an in-distribution and out-of-distribution data. If the feature extractor maps both of them to the same region in the feature space, we can very easily have overconfident predictions on out-of-distribution data. This is known as feature collapse. Naturally, we want to avoid feature collapse. One way of doing it is to impose a by-Lipschitz constraint on the feature space such that the distances in the input space are preserved in the feature space. In our work, we impose this by-Lipschitzness using architectures with residual connections and spectral normalization. There can, however, be other ways of achieving this as well. Once this constraint is achieved, one could think of having a distance-aware final layer like a radial basis function or a Gaussian process to quantify uncertainty in the last layer. In fact, two popular works, Deterministic Uncertainty Quantification or DUQ and Spectral Normalized Gaussian Process or SNGP, do exactly this to quantify uncertainty in a single model. However, DUQ and SNGP have multiple additional requirements or constraints. For instance, DUQ cannot scale up to a large number of classes, SNGP has additional hyperparameters, and both of them require many changes to the training setup. So we want to ideally formulate something even simpler. Let's say we have a sensitive and smooth feature extractor. We can easily get the features from the training set and create a simple feature density model on the corresponding features. This, in fact, forms the second component for our method. We find that a simple Gaussian discriminant analysis with a single mean and covariance matrix per class can suffice for effectively capturing uncertainty. We find that feature density thus computed effectively captures epistemic uncertainty, whereas the entropy of the softmax distribution from the same model effectively captures aleatoric uncertainty for ambiguous or noisy in-distribution inputs. Thus, now we have a simple algorithm for quantifying and disentangling uncertainty. For a given input, first we check the feature density. If it is low, then that indicates high epistemic uncertainty, and the input is out of distribution. If the input is not out of distribution, then we check the softmax entropy for aleatoric uncertainty. If the input has high softmax entropy, it is noisy or ambiguous. If it does not have high epistemic or aleatoric uncertainty, the model should be able to safely make predictions on the input. We call this simple method deep deterministic uncertainty, or DDU in short. For evaluating DDU, we use several popular OOD detection benchmarks and find that DDU performs competitively with deep ensembles consistently over multiple architectures and benchmarks. It outperforms general softmax probability as well as DUC and SNGP. One of the main applications of uncertainty quantifiers is in active learning, where we want to select informative points from a pool of unlabeled data to get labels from an oracle and train a model on such points. The goal is to attain high performance with a very small number of labeled samples. Even in active learning settings on MNIST and CIFAR-10, DDU performs competitively with ensembles and better than other baselines. However, when we include noisy samples in the training set, as is the more likely situation in real life, we find DDU's performance to have a steep increase compared to other baselines, which can't quantify epistemic uncertainty properly. The only baseline competitive with DDU in this setting is mutual information obtained from deep ensembles. Finally, we leverage DDU's simplicity and ability to quantify uncertainty from a single deterministic model to apply it to semantic segmentation on Pascal VOC. Even here, we find DDU to outperform other competitive baselines and even ensembles while requiring similar runtimes as a single deterministic model. Furthermore, we can qualitatively see that DDU's feature density captures epistemic uncertainty, being low on entire regions or objects which the model has not seen before, whereas softmax entropy captures aleatoric uncertainty, being high along the borders of objects. Thank you for watching this video, and please feel free to reach out to us over email if you have further questions.